Sebelum Anda membaca dan mendengarkan isi file kuliah yang didownload dari e-learning, perhatikan petunjuk kuliah yang saya tuliskan pada slide ini. Pertama, Anda harus mendownload materi kuliah tersebut dari e-learning Fakultas Teknik Unpas melalui akun masing-masing. Kemudian kedua, baca dan dengarkan file kuliah tadi. Jika masih belum jelas, maka baca dan dengarkan ulang. Jika masih belum jelas juga, maka catat hal-hal yang belum jelas tadi dalam bentuk pertanyaan-pertanyaan. Pertanyaan dapat disampaikan pada saat kita kuliah melalui video conference atau juga dapat dituliskan di WA Group. Banyaknya fluida yang mengalir di dalam sebuah saluran disebut sebagai laju aliran. Kita mengenal ada dua jenis laju aliran, yaitu laju aliran volume atau volume flow rate, dan yang kedua adalah laju aliran massa atau mass flow rate. Pada laju aliran volume, fluida diukur dengan satuan volume per satuan waktu. Sedangkan pada laju aliran massa, fluida yang mengalir diukur dengan massa fluida terhadap waktu. Apa perlunya mengukur laju aliran fluida di dalam sebuah saluran? Yang pertama, sebagai pengatur laju aliran atau pengatur aliran. Misalnya, untuk mengendalikan temperatur pada sebuah heat exchanger, kemudian untuk mengendalikan komposisi, misalnya pada sebuah reaktor, untuk mengendalikan ketinggian atau level cairan, misalnya cairan yang berada di dalam tangki, dan mengendalikan tekanan, misalnya tekanan fluida di dalam akumulator. Fungsi yang kedua yaitu untuk memonitor atau untuk mengawasi aliran. Jadi dalam hal ini, alat ukur tekanan berfungsi sebagai flow metering atau alat untuk mengukur besarnya aliran yang melewati suatu saluran. Alat untuk mengukur laju aliran disebut dengan flow meter. Terdapat dua kelompok besar dari flow meter, yaitu yang pertama jenis obstruktif, yaitu alat ukur laju aliran di mana di dalamnya terdapat penghambat laju aliran. Kemudian yang kedua, jenis non-obstruktif, di mana di dalam alat ukur itu tidak terdapat penghambat aliran. Di dalam kelompok obstruktif, ada 3 jenis flow meter atau pengukur laju aliran yang kita kenal. Yang pertama adalah differential pressure flow meter. Dalam kelompok ini terdapat orifice, nozzle flow meter, dan venturi flow meter. Kemudian yang kedua adalah rotameter. Ketiga, turbine flow meter. Untuk kelompok non-obstruktif, di dalamnya terdapat elektromagnetik, ultrasonik, dan cross correlation flow meter. Di dalam flow meter dari keluarga differential flow meter, kita akan melihat adanya komponen penghambat aliran fluida. Misalnya, di dalamnya terdapat pelat orifice. Pelat orifice ini seperti sebuah koin yang di tengahnya berlubang. Kemudian penghambat yang kedua berupa nozzle. Dan yang ketiga adalah venturi. Pada venturi ini kita melihat ada pengecilan penampang dari saluran. Akibat adanya pengecilan penampang itu, maka aliran akan terganggu atau terhambat. Pengukuran laju aliran pada differential flow meter ini sangat tergantung pada pengukuran tekanan yang dilakukan pada dua buah titik. Titik pertama diletakkan sebelum komponen penghambat dan titik kedua setelah komponen penghambat. Di kedua titik itu dipasangi pressure gauge untuk mengukur beda tekanan antara sebelum dan setelah komponen penghambat. Seperti yang kita lihat pada gambar, dua pressure gauge diletakkan sebelum dan setelah komponen penghambat. Pada slide ini kita melihat ada komponen penghambat berupa orifice plate atau plat orifice yang diletakkan di antara dua buah saluran. Plat orifice ini dijepit di antara kedua buah saluran. Kemudian pada saat fluida mengalir di dalam saluran, maka aliran fluida akan terhambat akibat adanya pengecilan penampang pada plat orifice. Kita lihat bagaimana air yang mengalir melalui plat orifice dimulai dari pipa bagian sebelah kiri mengalir ke sebelah kanan. Di situ kita akan melihat adanya pengecilan saluran sehingga aliran air akan terhambat oleh plat orifice. Kemudian setelah keluar, kita akan melihat air akan mengalir dengan sangat cepat. Kemudian setelahnya, air akan kembali pada kecepatan yang normal atau sama dengan kecepatan sebelum melewati plat orifice. Pada slide sebelumnya disebutkan bahwa pada orifice meter terdapat dua buah pressure gauge yang dipasang sebelum dan setelah plat orifice. Kita lihat pada gambar ini, Pengaruh dengan adanya plat orifis, tekanan dan kecepatan di antara sebelum dan setelah plat orifis akan menunjukkan angka yang berbeda. Tekanan sebelum melewati orifis lebih tinggi dibandingkan dengan setelah melewati orifis. Sedangkan kecepatan kebalikannya. Beda tekanan yang ditunjukkan oleh pressure gauge merupakan indikator berapa flow rate atau laju aliran yang mengalir di dalam orifice flowmeter ini. Ada rumusan matematik Q sama dengan K dikali akar delta P. Delta P inilah diambil dari beda tekanan yang ditunjukkan oleh pressure gauge. Kemudian K ini merupakan sebuah konstanta yang nilainya tergantung pada ukuran plat orifis dan juga jenis fluida yang mengalir di dalam saluran. Dengan memasukkan nilai tekanan dan konstanta, maka kita bisa mendapatkan berapa laju aliran dari fluida yang mengalir di dalam saluran. Alat ukur laju aliran yang kedua disebut dengan rotameter. Jika kita melihat gambar pada slide ini, kita akan melihat ada sebuah tabung yang di dalamnya berongga, di mana bentuk dari rongga itu adalah kerucut, mengerucut di bagian bawah penampangnya lebih kecil dibandingkan dengan bagian atas. Jika fluida mengalir dari bagian bawah rongga ke bagian atas, kemudian di dalam rongga ini terdapat sebuah komponen yang melayang, maka akibat dari tekanan fluida yang mengalir di dalam rongga, maka komponen yang melayang ini akan bergerak sesuai dengan laju aliran yang melewatinya. Jika semakin banyak fluida yang mengalir di dalamnya, maka komponen yang mengapung akan cenderung bergerak semakin ke atas. Besarnya laju aliran itu akan terbaca pada skala yang ada di sebelah kanan atau kiri, di mana komponen pengapung itu akan diam. Biasanya tabung rotameter ini terbuat dari kaca atau plastik yang transparan sehingga kita bisa melihat fluida yang mengalir dan komponen pengapung yang bergerak naik turun di dalamnya. Alat ukur ini bisa digunakan untuk mengukur laju aliran gas ataupun cairan yang kita mungkin pernah melihatnya jika rotameter ini dipasang pada sebuah tabung. Prinsip yang digunakan pada rotameter ini berdasarkan gaya gravitasi dari berat komponen pengapung dan gaya momentum dari fluida yang mengalir di dalamnya. Jika kedua gaya itu seimbang atau balance, maka komponen pengapung akan diam di satu posisi. Jika gaya akibat momentum dari fluida lebih besar dari gaya gravitasi, maka komponen pengapung ini akan cenderung naik ke atas. Dan sebaliknya, jika gaya gravitasi lebih besar, maka komponen pengapung ini akan cenderung turun ke bawah. Naik turunnya komponen pengapung ini menunjukkan berapa besar laju aliran yang mengalir di dalam rotameter. Alat ukur laju aliran ketiga yang memanfaatkan prinsip obstruktif adalah turbine flow meter. Pada gambar di slide ini kita melihat ada komponen baling-baling di dalam flow meter, dan baling-baling ini akan berputar jika ada fluida yang mengenainya. Pada saat fluida mengalir melalui turbine flow meter ini, baling-baling akan berputar, kemudian putaran dari baling-baling ini proporsional dengan kecepatan fluida yang mengalir atau yang melewatinya. Kecepatan jika dikalikan dengan luas penampang dari saluran, maka kita akan mendapatkan laju aliran volume.
In this first video of a two-part series, we're going to introduce you to flow measurement using a differential pressure transmitter. The second part of our two-part series will take you through the process of checking the output accuracy of a differential pressure flow transmitter and show you how to recalibrate it if necessary. Before we get started, you might want to review two of our other videos, Differential Pressure Transmitter Explained and What is Sensor Calibration and Why is it important? You can find the links to these videos in the description. Flow transmitter calibration is the focus of our discussion, but let's review some other important terms first. We're going to define the terms range and span and zero in span adjustments. After that, we are going to explain how a differential pressure transmitter is used to measure the volumetric flow rate, explain why a square root extractor is needed in differential pressure transmitter flow measurements. Okay, let's go. We say that an instrument is calibrated when its output corresponds to a specific input across a specific range of inputs. Said another way, instrument calibration is a process where the instrument is adjusted in order to achieve the desired output range for a specific input range. For example, a current output type flow transmitter is calibrated for a volumetric flow range of 30 gallons per minute to 100 gallons per minute. When the transmitter produces a current output of 4 milliamps at 30 gallons per minute and a current output of 20 milliamps at 100 gallons per minute, a flow rate of 65 gallons per minute would produce an output of 12 milliamps. The input span of an instrument is simply its lower range value, often referred to as LRV, subtracted from its upper range value, often referred to as URV. For example, the span of the input range of 30 gallons per minute to 100 gallons per minute is 70 gallons per minute. Zero and span are the names of the adjustments made in order to calibrate an instrument. There are many ways to adjust zero and span. For example, they could be physical adjustments, such as potentiometers, or software-based push-button adjustments. A common method of flow measurement is done by using a differential pressure transmitter. The differential pressure transmitter, often referred to as a delta P transmitter, is placed across an obstruction such as an orifice plate. The orifice plate will cause a varying differential pressure drop across it as the flow through the pipe changes. Unfortunately, the differential pressure across the orifice is not proportional to the flow rate, but is actually proportional to the square of the flow rate. That's why in applications like this, we need a square root extractor. Sometimes this square root function is built into the transmitter, and sometimes a square root extractor is a separate signal conditioning instrument connected to the output of the transmitter. Do you remember when we said that the differential pressure is proportional to the square of the flow rate? In fact, the volumetric flow rate is directly proportional to the square root of the differential pressure. You might have seen this equation before, where Q is flow rate, and delta P is the differential pressure across the orifice. Let's do some math and see what happens. According to the equation, a flow rate of 90% would produce a differential pressure of 81%. There is a way for the flow rate to be directly proportional to the differential pressure, and that's by removing the square root from the equation. A square root extractor will perform this function. If you're still a bit fuzzy, it will all become clearer as we progress to part 2 of this video series. Let's review what we've discussed. An instrument is calibrated when its output corresponds to a specific input across a specific range of inputs. The input span of an instrument is simply its lower range value subtracted from its upper range value. Zero and span are the names of the adjustments made in order to calibrate an instrument. A common method of flow measurement is done by using a differential pressure transmitter across an obstruction, such as an orifice plate. The differential pressure across an orifice is proportional to the square of the volumetric flow rate. Therefore, we need a square root extractor. Be sure to download the RealPars app. When you download the app, you'll be able to watch an entire free course on PLC hardware. Just like this video, the lessons are all high quality and also very easy to follow. By downloading the RealPars app, you have access to a wealth of practical knowledge as an automation engineer right in your pocket. And you'll also receive new, fresh out of the oven videos each and every week.
Easy to install, simple to use, reliable, accurate and inexpensive. What more could you want from a variable area flow meter? Achieving a balance between all of these customer benefits is an art in which Krone excels. Variable area flow meters are suitable for measuring liquids and gases. They have an upright conical tube in which a sophisticated float moves freely up and down. The flow through the tube causes the float to rise until the forces are in equilibrium. The flow rate is read off from the scale at the level of the float. The glass measuring cone allows direct reading of the float movement, whilst meters with a metal cone have a magnetic pickup. There is no need for external power for readout. For almost every application and industry, Krona produce an enormous variety of variable area meters. In fact, a new Krona VA meter is installed somewhere in the world every 4 minutes. Krona variable area flow meters are precision built. Extensive quality control during the entire manufacturing process ensures that cones and floats are within tight tolerances. The welding is fully automated, including inline testing. Every meter is wet calibrated in a fully automated video-based calibration rig to produce perfect results without any chance of human error. Krona customers are able to extend the functionality of their variable area flow meter by simply adding one or more modules. Limit switches, signal converters with analog and digital output, counters, all fitted on-site without turning down the process in minutes. Krona variable area flow meters are easy to install and use. They cost substantially less than other technologies, both to buy and to maintain. Rediscover this reliable, versatile and inexpensive technology. Variable area flow meters from Krona.
In this video, we're going to discuss a very common flow measuring device called a turbine flow meter. Depending on who you talk to, a turbine meter has one or two major parts. Some will tell you that the turbine meter has only one part, the mechanical component. Others will refer to a turbine meter as having two parts, the mechanical component and the electrical component. In this video, we'll consider the turbine flow meter as a two-part device. All right, let's go. First of all, let's talk about how a turbine flow meter works. A turbine flow meter is inserted in a pipe directly in the flow path. The mechanical part of the turbine flow meter has a turbine rotor placed in the path of a flowing stream. The only moving part of the turbine meter is the mechanical rotor. The rotational speed of the rotor depends upon the flow velocity. The rotor blades are usually made of stainless steel. As the rotor spins, the passage of each rotor blade past a pickup point will generate an electrical pulse. The electrical pulses are created in different ways, depending upon the rotor blades themselves and the pickup unit characteristics. In most turbine flow meters, magnets are fitted to the blades, and a magnetic pickup sensor is used to create the pulses. The higher the rate of flow, the faster the rotor turns, and the greater the number of pulses. The shape and the voltage level of the generated pulses depend entirely upon the type of pickup unit used. The electrical pickup sensing device could be a simple two-wire passive magnetic pickup producing an AC type output. The electrical pickup sensing device could be a three-wire active device, such as a Hall effect sensor, that produces cleaner and more uniform square wave pulses. As we said earlier, the turbine rotor will turn at a different speed depending upon the fluid flow velocity. Fluid velocity is a measurement of the distance a particle of a substance traveled per unit of time. Typical velocity units are feet per second or meters per second. Fluid velocity plays a very important role in the operation of a turbine flow meter, but in most applications, a turbine flow meter is used to measure volumetric flow rate. Volumetric flow rate indicates the volume of fluid that passes a point in a unit period of time. If you could count the number of gallons of liquid flowing past a certain point in 1 minute, you would be able to state the volumetric flow rate. Volumetric flow rate is expressed in units such as gallons per minute, or GPM, cubic meters per second, and cubic feet per second. Okay, so now we've reviewed fluid velocity and volumetric flow rate. Let's talk about how a turbine flow meter is used to measure volumetric flow rate. When you buy a turbine flow meter, it should arrive with a tag or a calibration certificate declaring its K factor. This K factor is unique to each and every turbine flow meter and is determined by the manufacturer. As we discussed earlier, the turbine flow meter will generate pulses, and the pulse rate depends upon the fluid velocity. The unique K factor declares the number of pulses that will be generated for every unit of product passing through it. K factor will be expressed in terms of the number of pulses produced, such as 150 pulses per gallon. Let's assume we are using a turbine flow meter to measure flow in gallons per minute, or GPM. This turbine flow meter has a K factor of 3 pulses per gallon. Recall that the unit for frequency measurement is hertz. 1 hertz is equal to 1 cycle per second. With that in mind, we say that the turbine flow meter produces a frequency of pulses per second, which we express as hertz. If we have a K factor of 3 pulses per gallon, the output frequency at a volumetric flow rate of 200 gallons per minute, or GPM, is 10 hertz, or 10 pulses per second. If you're wondering where we derived these values, we've included a very handy K factor calculator for you to use. You can find the link to this K factor calculator file in the video description. We can connect the turbine flow meter to a PLC frequency input card. The input frequency now represents the volumetric flow rate. If we are troubleshooting or performing loop calibration, we can use a calibrator with a variable frequency output to simulate the turbine flow meter. Here's an example of a turbine volumetric flow rate measurement loop. A 2-wire passive sensor pickup unit produces AC-like pulses, which are conditioned by an amplifier, before being sent to a high-speed counter PLC input module. Typical installation requires 10 pipe diameters upstream of straight pipe and 5 pipe diameters downstream. The turbine meter can only be used in clean, lubricating fluid, because suspended particles can easily damage the device. The turbine rotor must be positioned in the exact center of the flow, and laminar flow is critical, often requiring straightening vanes. Even though they are one of the most accurate volumetric flow meters in use today, they do have some downsides. The K factor is not always consistent across the entire flow rate measurement range. Turbine flow meters are not accurate at very low flow rates. Viscosity is an issue, as thicker or thinner fluids can change the rotor speed and affect the meter's calibration. Keep in mind that the turbine flow meter K factor was determined at the factory using a specific set of parameters. They are not recommended for steam. As with other mechanical devices, the rotor bearings wear out. In what industries are turbine flow meters used? Considering their popularity, a better question might be, in what industries are turbine flow meters not used? You will find turbine flow meters in oil and gas, including fracking, water and wastewater, chemical, power, food and beverage, aerospace, pharmaceutical, and pulp and paper. If you want to learn more, you might want to review 3 of our other videos: how flow meters work, what is sensor calibration and why is it important, and what are 2-wire and 4-wire transmitter output loops. You can find the links to these videos in the description. Okay, let's review. A turbine flow meter is inserted in a pipe directly in the flow path and has a turbine rotor placed in the path of a flowing stream. The higher the rate of flow, the faster the rotor turns, and the greater number of pulses generated by an electrical pickup. In most applications, a turbine flow meter is used to measure volumetric flow rate. Every turbine flow meter has a unique K factor stating the number of pulses that will be generated for every unit of product passing through it. There are several important issues to consider when installing a turbine flow meter. Considering their popularity, there are very few industries where turbine flow meters are not used. Want to learn PLC programming in an easy-to-understand format and take your career to the next level? Head on over to realpars.com.
Digital innovation. Unmatched noise immunity. The Siemens ultrasonic flow meter solution. Best-in-class performance and day-to-day operation for all liquids and pipe sizes. Sound is a series of mechanical vibrations transmitted through a medium. Given the delay in transit time, some animals use ultrasound with more than 20,000 Hz, not audible to the human ear, to estimate distances extremely well. Think about an object moving in the same direction as a moving sidewalk. It advances at a faster pace than an object traveling in the opposite direction. In a flow system, sound waves behave in the same manner. Combined ultrasonic transmitters and receivers are placed opposite each other. Ultrasonic waves are alternately sent and received by means of the piezoelectric effect, where mechanical energy is converted into electrical energy through the use of a crystal. When moving in the same direction as the flow, they travel faster than waves traveling against the direction of the flow. The higher the flow velocity of the medium, the greater the difference between the two transit times. Combined with the known area inside the pipe and the measured sonic velocity and temperature of the media, it is possible to accurately measure the volume and also to derive parameters like density and viscosity. As the flow meters have no parts that wear, measurements remain constant and the total cost of ownership low. The inline product family measures with very high accuracy. The sensors are in direct contact with the medium. The clamp-on version, however, uses sensors that are mounted on the outside of the pipe. Ongoing processes are not interrupted and the sensors never touch the medium. Siemens offers a wide range of solutions, from single-path transit time to highly complex multi-path measurements used in demanding applications where performance may be affected by flow profile distortion. If the medium contains dispersed particles or bubbles, Siemens uses a method based on the Doppler effect, a frequency shift similar to a passing fire engine. When an ultrasound wave hits the particles, the sound waves are reflected and the wavelength shifts based on the particle's speed. The faster their speed, the greater the frequency shifts. To guarantee maximum measuring accuracy, even if the state of the medium changes, Siemens has developed a combined transit time and Doppler mode method, enabling automatic switching. Digital innovation, ultimate noise immunity. C-Trans FS. Digitize your productivity.
Flow measurements are essential to running a plant efficiently and safely. There is an array of flow technologies available to make these measurements, including the electromagnetic flow meter, oftentimes referred to as a mag meter. Mag meters are selected because they are obstructionless, cost-effective for aggressive chemicals and slurries, and provide a highly accurate volumetric flow measurement. Mag meters are comprised of a transmitter and sensor that together measure the flow. The mag meter sensor is placed in line and measures an induced voltage generated by the fluid as it flows through the pipe. The transmitter takes the measured voltage generated by the sensor, converts the voltage into a flow measurement, and transmits that flow measurement to a control system. To make the flow measurement, the mag meter utilizes a set of coils and a pair of electrodes. The mag meter's coils are driven by the transmitter with an applied current. Once powered, a magnetic field is formed between both coils. Once the pipe is full and the fluid begins to flow, the force of the magnetic field causes the negatively and positively charged particles of the fluid to separate as they pass through the magnetic field. This separation causes an induced voltage to be formed between the electrodes and the sensor. The conductivity or charge of the fluid in the pipe must be at a certain level for the transmitter to measure the induced voltage at the electrodes. This flow principle is known as Faraday's law. mathematically defined by the equation E equals K B D V, where the induced voltage E is directly proportional to the velocity V of the fluid moving through the magnetic field B. The induced voltage is carried to the transmitter through the electrode circuit. The transmitter then converts this voltage into a quantifiable flow velocity. With the known velocity along with the area of the pipe, the volumetric flow rate of the fluid is calculated. To prevent electrical shorts of the sensing component circuitry, the pipe of the flow meter is lined with a special material known as a liner. This liner, along with a selection of the proper electrode materials, is important to protect the sensor against abrasive and corrosive chemicals and solids. One historical limitation of magmeters is the impact of process noise. Process noise occurs when particulates impacting the electrode interfere with the induced voltage measurement, generating a false reading. Rosemount has become a true expert regarding material compatibility for appropriate liner and electrode selection, and has advanced digital signal processing software to provide maximum measurement reliability for even the most challenging applications. Emerson Flow Measurement Technologies for all your application needs.